So welcome everyone for the session on foundation models for PDEs. So this talk is given with Maximilian Herde. So he did his bachelor's and master's at ETH Zurich, and he's been working with Sid Mishra and other collaborators on Poseidon, which is, in my opinion, one of the most diverse uh, effort towards foundation models for PDEs. And he'll be joining us next week here in person for the hackathon. So that'll be another chance to interact with him. With that short introduction, Max, take it away.
Thanks a lot for the introduction. Thanks a lot for the invitation. I'm very happy to be here and present our work on foundation models for PDEs that we did at the Computational and Applied Mathematics Laboratory at the ETH Zurich under Sid Mishra's supervision. Maybe I just want to go briefly over our collaborators. So we were 7 people in total. Some working on data sets, some working on architecture and training, and yes, all under the supervision of Sid Mishra on the right. So I just want to quickly start on, maybe it's a bit too easy, but still start on why we need something for partial differential equations, why we need a foundation model for partial differential equations, because, well, partial differential equations model many physical phenomena, let it be from very large scale star collisions in astrophysics to weather or climate, as we've seen before, or let it be structural engineering problems where you can also utilize partial differential equations, or to very small scale problems where you can utilize, for example, the Schrödinger equation to model atoms. So, but the problem is with classical numerical methods, they may be very expensive. Most of you probably know that. And that hinders sometimes many query problems because of this expense, such as uncertainty quantification or inverse design. But this is where machine learning can come in, because these machine learning models have very fast inference time. So once you train the machine learning model, and you fitted it to your problem, you can utilize the model over and over, such as in weather, for example, where when a machine learning model for weather is trained, you can do inference, as we've heard before, relatively quickly on a laptop and get a weather forecast. And prior to machine learning models, this took 2 hours on a supercomputer. So there's a lot of promise in these models. And what was done before, I guess most of us are familiar with it, is operator learning in this domain. So where you take data from PDEs and learn a data-driven model to compress a solution operator of a PDE on a specific data distribution on a specific PDE. So for example, we can go from one input function to an output function. So this is what an operator is. For example, here what is seen as a shear layer problem from the incompressible Navier-Stokes equations, where you have some input function that is the x velocity at time 0, and you want to learn the output function, which is the x velocity at time t. So in principle, very specific through one specific data distribution. So you will have in your data set a lot of these shear layers, and then you will get the output functions. And then you will learn a supervised model to get the solution operator to this specific data distribution and PDE. I guess most of us know the most prominent methods. FNO, the most known one, Fourier neural operator, which utilizes the Fourier space to learn this mapping, or from our group, the convolutional neural operator, short CNO, or deep ONet, for example. But there's much more. not enough time to list them all, I guess. But yeah, as I said, until now, this is very limited. You train on a single data distribution, on a single PDE, and most of the time you need a lot of samples. And as I said before, it may be very expensive to gather a lot of samples because, well, simulating may be very expensive. For example, in fluid dynamics, it takes very long. As I said, for weather, for example, the numerical weather models take sometimes 2 hours on a supercomputer, which is not practical if you need many samples for complicated problems. So it may be of interest to get a model that is trained on multiple data distributions, and maybe even on multiple PDEs, which we could then call a foundation model for PDEs. But maybe let's take a step back and ask what is a foundation model really? So what is the actual definition, or what do we actually need to do to call a model a foundation model? So for that, I just went to well, I guess what everyone does nowadays, to ChatGPT, a foundation model, and asked what is a foundation model. And ChatGPT gave me a quite long answer, but I guess the most important points are in there. So it's a model that is pre-trained on a broad set of data and that can be adapted to a wide range of downstream tasks. And this is what we're going to do. So we're going to pre-train a model, as seen before with Aurora, on a broad set. Well, we will have to define what a broad set of data means for PDEs, and that we can adapt to a very wide range of downstream tasks for PDEs. This means different data distributions, different PDEs, maybe different physics. And it's characterized by its large scale, both in terms of data it's trained on and the number of parameters it contains. So yes, with that in mind, the probably biggest question comes up: is this even possible in this kind of operator learning sense to create such a model, such that it can solve PDEs, a general model for PDEs or even for physics? So in order to answer, or to at least partially answer this question, we went forward and built an architecture for that. Well, we took inspiration from computer vision, as it's mostly the case, to build a model for two-dimensional problems, two-dimensional in space, as you can see here. For example, velocities of the Navier-Stokes, of the two-dimensional incompressible Navier-Stokes equations as they are depicted here. And we wanted to build a model that is time-dependent, so where we can give it a time and it should give us the solution at a specific time. So we took inspiration from computer vision. Specifically, we took a vision transformer, and not the classical vision transformer, but the shifted window vision transformer, as was also done with Aurora, but the 2D version here, and build a UNet-style architecture. So we tokenize the input by patching, as is always done with vision transformers. I hope you can see my cursor. So if you have your input function, your two-dimensional input function in space, you tokenize the initial condition, as can be seen by these white borders. So you patch it, then you embed these patches into latent space, and then you feed the sequence of these patches to the shifted window vision transformer, which then will downsample, and in the decoder will upsample again until all the tokens reach the recovery stage, where you get back your output function that is hopefully transformed in a reasonable manner. So with that, you kind of get a latent model, and I have to mention that, or I have to stress that, linear embeddings and linear recovery and mix-up layers. So maybe to go a bit more into detail, I don't know if this has been done before, but just go into detail into that, into the Swin transformer block. So this is the backbone, more or less, of the architecture, the transformer that we used here. So we actually used the Swin version 2 transformer, which doesn't use dot product attention as in the classical transformer, but scaled cosine similarity, just to help with scalability. And also we utilized just a relative position bias to enforce spatial, to encode spatial information into the sequence of tokens. And then what we do to add time to our model, we just said we can just condition our model at every layer norm, because we have a lot of layer norms in the model. We can just give to the layer norm a lead time. So we have the initial condition, which just depends on space. We just have one, so there's one snapshot, there's one initial condition, and then we give to the model a lead time and tell the model in this way that we want the solution at this specific lead time to these time conditioned layer norms. So this is basically, we take the layer norm as we know it. Normally it's just alpha and beta, so gain and bias. And we replace gain and bias by a conditioned version of them, which is just an affine embedding of the lead time. And that is done, basically we switch out every layer norm in our whole model. So it's in every transformer block, we have 2 layer norms, and every one of those is switched out through this lead time condition layer norm. And this way we can get a time-dependent model, time-dependent and 2-dimensional in space. And then we train it in a special manner, well, not really special, but we say, well, when we have our simulations of PDE data, we either way in a time-dependent version have the whole trajectory available if we create the data. So why not use all the snapshots during training? So we kind of called this all-to-all training and just said, well, let's train in a supervised manner on all possible physical combinations of solution snapshots, and just show the model during the training process that we all possible combinations of time steps. So we can go from T0 to T1, or we can go from T0 to T0, or we can go from T0 to T. So the model kind of learns all possible time steps, which in the end means that when you do inference, the model has seen a lot of different time scales basically through this with the given lead times. And we can, at inference, not just to get to our final time T, do just a single lead time input, but we can also do many small steps and basically use it as a conventional solver kind of. In this case, it's not bound to the CFL condition as would be in a conventional numerical solver, which is a neat thing that I just wanted to mention.
So just to make sure I understand, so you're using time as a scalar input? Is that what you're saying?
Yes, exactly. It's time as a scalar input, then you transform it through an affine embedding at every layer norm through different affine embeddings. So every layer norm has its own parameters. And through that, it's conditioned. So you will just have your initial condition, you give the model the initial condition and time or lead time as an input, and the model should, in principle, give you as an output the solution at lead time T in this case. So with all that in mind, this is basically the architecture and the training process. So how we handle time-dependent solution operators. The most important thing probably is the data. As always in deep learning, you need high-quality data. So what did we do? Well, for PDEs, if you want to build a model that should understand many PDEs, where do you start? So what do? You have to create the data at some point. You just can't scrape the whole internet and just train on it as was done with all these LLMs. So you just can't get out and get all the data that is out there. You have to create it on your own. So we thought about, well, what do? We can just start with some sort of PDE or some set of physics and then check if we're kind of able to generalize to something that was not seen. So what we did, we started with fluid dynamics. More specifically, we started with incompressible fluid dynamics and also with compressible fluid dynamics. And we took 6 different data distributions, 2 from incompressible Navier-Stokes equations and 4 from the compressible Euler equations that are very rich in terms of their features and are, in principle, if you learn them from scratch, let's say with an F and O, are very hard to learn because it's very multi-scale in nature, the problems, and there's a lot going on. So you can see here on the left-hand side, we have in the initial condition, it's a mixture of sines, multi-scale sines, and on the right-hand side, it's a mixture of Gaussians. So these are the 2 data sets that we use for pre-training with the incompressible Navier-Stokes equations. And maybe it's important to notice, so we generated about 20,000 trajectories each for each of these data distributions with 21 snapshots each. So together with the compressible Euler data, we get about 80,000 trajectories. So there we have 10,000 trajectories for each of these data distributions. And here I have to note that these are much more complicated than we have seen before, because now with the compressible Euler equations, we can see shocks and many vortices going on. So we will have 4 different data distributions, as mentioned before. Now we are interested in also the density and the pressure, because the density is now not constant and the pressure is not linked to the velocities anymore very strictly. And we have 4 different operators. One where we start, maybe I have to stop this at the initial condition, where we start with a mixture of curved, piecewise constant curved initial conditions, which if you started the simulation will evolve in many shocks and multi-scale vortices. So it's a very complex solution, and it takes a long time to generate this if you do it with a conventional solver. And then we have standard Riemann problems here in the middle, 4-quadrant piecewise constant initial condition, and then you will evolve shocks along the trajectory, as you can see. And then we also have a Kelvin-Helmholtz instability. You see very large scale vortices in the density. Kind of also here a shear layer type problem. And then again, we have Gaussian, a mixture of Gaussians as initial condition. So as I said before, here we have incompressible Navier-Stokes equations and compressible Euler equations. So we just took problems. So we just took PDEs from fluid dynamics and data distributions thereof, and just decided let's just start with these and try what happens. Maybe the features are rich enough and we can do something with it, with the model afterwards. So maybe to go into detail a bit more about pre-training, we do standard supervised training, so nothing fancy, with relative L1 loss to balance out the different variables we had. So you've seen it before. We had velocities for the incompressible Navier-Stokes equations and density, velocities, and pressure for the compressible Euler equations. And well, you might have noticed it. So we mix all these. For one, we just have velocities. For the other, we have 4 different variables. So what do we do during pre-training? We have to fit all these in one batch. And we have to mix these. So what we did is we just added the incompressible flow data with 1s in the density and in the pressure variable. And because it's incompressible flow, it makes sense for the density. It's constant. So the model kind of learns that it's an incompressible flow through this constant density that we give to it. So it can, or it should be able to distinguish between incompressible and compressible flow kind of intrinsically through the data. And we mask out the pressure because we didn't have it available for the incompressible flow data. And after pre-training, we call this model Poseidon, just to give it a cool name. And then we went
So
on.
Max, a quick question. Do you do anything special to scale the different variables, or
No, we
because they
kind
may
of,
have different magnitudes in the different data sets, right?
yes. So we do normal classic normalization before training of
Okay,
the
so
data.
just statistical normalization.
Yes,
Nothing.
exactly.
Yeah.
Mean variance, nothing fancy.
Okay. All right.
Yeah.
But different data sets may have wildly different means and variances, right?
Yes, but since we generated the data on our own,
It's under control.
Yeah, exactly.
Okay. Got it.
So after pre-training, we kind of went on and said, well, now we really have to take this model at a test or at multiple tests, and just said, well, it makes sense. If we really want to build a foundation model, we really need to go out of distribution from the pre-training data. So it really must be different. We really want to see if the model has seen features that are helpful for all kinds of downstream tasks. So we said we want a wide range of data distributions and a wide range of PDEs in the end to test the model on and fine-tune it on. So we have the pre-trained model, and now we go on for fine-tuning and fine-tune it with a little data on a lot of, actually in the end, it's 15 downstream tasks that are comprised of one, different data distributions from the incompressible Navier-Stokes equations. So it's not very different in terms of the PDE, but the data distributions are very different. Then we also add forcing to the incompressible Navier-Stokes equations. So the model hasn't seen this during pre-training, but there was no forced data. We also add scalar transport. So just a passive scalar that you put into the flow and let it be affected by the flow. In addition to the incompressible Navier-Stokes equations, so there's new physics and also a new data distribution the model hasn't seen. Then we also changed data distributions in the compressible Euler equations and also added gravitation there. It's in the same sense as forcing. There was no forcing for the compressible Euler equations during pre-training as well. So why should it be able to utilize features from the pre-training data for gravitation? So we also have a data set for that. Then we also went out of distribution in PDEs, and well, really out of distribution because there's no PDE added. It's completely different PDEs. So we checked with the acoustic wave equation with two different data distributions. We also checked with the reaction diffusion equation, the Allen-Kahn equation that you can use in material science. We also checked with a time-independent equation, the Poisson equation, which is pure diffusion. And maybe I have to mention that, but for the fluid dynamics data, it didn't really see diffusion, any type of diffusion, because we simulated the implicit limit. And then we also checked with the also time-independent Helmholtz equation. So it's important to note we pre-trained a time-dependent model, and we can also fine-tune to time-independent models, as we can see later on now when I'm going to show the results. So maybe to go a step back, what do we actually mean with fine-tuning in this context? When we have a pre-trained PDE model, well, we want to utilize the representations from the pre-trained model, and we only want to slightly change the parameters of this model. So we want to really hope that the pre-training gave us very good representations to utilize maybe for different physics. So we just change the model parameters with a very low learning rate, basically, which assumes that we have good representations in the first place through pre-training. So, and again, here comes the question. We have fluid dynamics pre-training data. Why should this even work with, let's say, a wave equation, which is very different to fluid dynamics data? So now maybe on our model itself, how does this look like in a concrete way? So we have this unit style architecture, as I said, with this latent model here with all the transformer blocks. And then we have these linear embeddings and recovery, which take the input and get where we can get the output from, the output functions. So natively, if you just have a fluid dynamics problem where you have density, velocities, or pressure, you can just transfer all parameters and use the model as is. So you just take the pre-trained model, initialize all parameters with the pre-trained model's parameters, and just fine-tune on a little bit of data of your problem with a small learning rate. But then comes the question, what do we do when we have the wave equation, for example, where you have the wave propagation speed as input and the solution displacement field initial condition maybe, and you want to output the solution at time t, at lead time t. So you have different variables. What do you do? I mean, the model expects density, velocities, and pressure. So we thought it makes sense. Well, we have linear embeddings here and linear recovery to get our output. So we just transfer all the latent parameters. And we have to, because the variables are different, we have to switch out the embeddings and train these from scratch. But yeah, so this is basically the procedure if you switch out the variables, if you have different physics. You will have to learn the embeddings from scratch with high learning rate because random initialization, but use a low learning rate for the later model because we hope, again, that we have good representations there. And then we went on, and after pre-training and fine-tuning on all these tasks, we always evaluated the model on scaling plots. So we always looked at how does our model perform with different numbers of training trajectories. So what's our test error from the whole test set when we train with a different number of trajectories? Because we want to see how efficient we are in terms of training trajectories that we need. So here, this is a result plot for the incompressible Navier-Stokes equation, specifically for the shear layer problem that we've seen before. Again, I want to stress this is different to the pre-training data. You've seen the pre-training data. There's nothing that looks like this shear layer in the pre-training data, apart from maybe the Kelvin-Helmholtz instability. But again, this is compressible flow. So still, you could argue maybe it's a bit in distribution, but you will see. We can also go out of distribution. So here, we tested multiple models. So we have the standard F&O that we train just on the downstream task. So from scratch, from random initialization, we take an F&O, we train it also with this time conditioning just on the downstream task. Yeah. And then we also take our architecture and train it from scratch. That's denoted as SCOP, the scalable operator transformer. Train it from scratch just on the downstream task as a baseline. Then we also take the convolutional neural operator, train it from scratch just on the downstream tasks with these numbers of trajectories. And then we have our models in different sizes, base and large. And we also have a tiny one, which we don't show because the plot will get very cluttered. And a foundation model variant of the CNO, where we basically take the same pre-training data, the same pre-training procedure, and pre-train CNO, and then fine-tune CNO. And then also something from the literature, the paper is called multiple physics pre-training, where the weights are available. It was pre-trained on a mixture of fluid dynamics, reaction diffusion, and Scholler water equations, if I'm not mistaken. So we took these pre-trained weights and fine-tuned on our problems. So we have multiple baselines and also our models. And as you can see here, well, we're a lot more efficient in terms of number of training trajectories on the downstream tasks. And well, one could argue we can utilize the representations from pre-training. And also what we can see here, the architecture and pre-training data seems to be very important for for fine-tuning. I will answer or try to answer the questions after the talk, if that's fine, because there's one in the Q&A. Oh, sorry. That. Can you give me a second?
Yeah.
So
no, yeah, go ahead.
Yeah. And since we have 15 downstream tasks, as I said earlier, it's hard to look at all of these plots. So we kind of came up with two different metrics we wanted to look at. One is kind of this gap, this horizontal gap between a baseline, for which we chose FNO because it's the most widely known one and the most widely known neural operator. And always compare the error at a specific number of training trajectories that FNO uses, and search for the same error on the scaling plot of all the other models, and compare this ratio to find how our sample efficiency gain is. So how many samples do we need to reach the same error as FNO at a specific number of trajectories, which was, I think, 1024. And then we also looked at the second number, this vertical gap, the accuracy gain between FNO and all the other models. So with a specific number of fine-tuning or training trajectories, how much accuracy do we gain? And which we call it accuracy gain, of course. And with that, we fine-tuned all our models. And we can see now in this immense table that we kind of outperform all other models, all pre-trained models, and all models that were trained from random initialization in terms of sample efficiency and accuracy gain. And maybe I have to explain what all these abbreviations mean. So NS stands for the incompressible Navier-Stokes equation, here piecewise constant initial condition. Then we have a sinusoidal vortex sheet initial condition, a Brownian bridge initial condition, the shear layer as mentioned before. Then with Navier-Stokes tracer, we add a passive tracer as mentioned before to the flow. So new physics here. We are still able to outperform everything. We add forced Navier-Stokes, a Kolmogorov flow. Here with the compressible Euler equations, we have a Riemann problem with uncertain interfaces. We have a Richtmeier-Meshkov, a standard benchmark, a Richtmeier-Meshkov simulation from compressible Euler equations. We also have steady Euler equations, where we map from an airfoil shape to the steady state density over the airfoil shape. And there you can see that the model is not the best in this case. We add gravitation to the compressible Euler equations with the Rayleigh-Taylor benchmark. Then with the wave equation, we have a layered medium, we have a Gaussian medium, the Alenkane equations, and then Poisson with Gaussian source term and the Helmholtz equation. And as you can see, well, the farther you go out from the pre-training data in terms of distributional, the less impressive the results are. But still, if you switch or if you change the physics, for example, for the wave equation, you still outperform everything. So we really found that by pre-training on fluid dynamics data, it seems that we can really utilize that to fine-tune on different physics. And yes, as I said, well, the SEAF, this airfoil data set, we're not the best here, maybe because well, this is a non-Cartesian domain anymore. We map from a shape to steady state density. So it hasn't seen it, and it's much harder. And yes, I just want to mention that again, here we see that really the architecture is important. And And the pre-training data is also important. So MPP has different pre-training data, and CNO is a different architecture, but the same pre-training data. So you can really see that the model is able to do something. And maybe to go a bit more visual, because these are numbers, it's not very clear what's going on. Just want to go into some case studies and look at different problems. So here we look at this kind of initial condition. Again, a 4-quadrant Riemann problem, but with the compressible Euler equations, so fluid dynamics again. So not really much out of distribution from the pre-training data, but here you have uncertain interfaces, which will lead to vortices, vortex roll-ups in the trajectory going on. And if you then look at the model, at the model predictions, so on the left side we have the ground truth with the density, the velocities, and the pressure, and then we have zero-shot prediction, fine-tuning with one trajectory, so just a single one, then with 4, 32, and 128. And as you can see, well, zero-shot prediction doesn't really work. But still with one trajectory, you get something that kind of resembles the solution. And as you go on with the number of trajectories that you give to the model, during fine-tuning, you will see that it's quite able to resolve shock locations and the vortices and the vortex roll-ups. And it doesn't really need many trajectories. So 32 is not much. As you can see, the prediction is already quite good. So now it might be of interest to look into where does this come from. Here we have compressible Euler equations, so we can kind of interpret what's going on, because this is, well, it's a PDE that was also seen during pre-training. So what we did then is we halved our pre-training dataset just in terms of quantity, and compared this kind of pre-trained model to a model that was pre-trained on a less diverse pre-training dataset, where we took out 3 out of these 6 data distributions that we've seen earlier. One from the incompressible Navier-Stokes equations, this multi-scale sinusoidal flow, and 2 from the compressible Euler equations, namely this very complex curved Riemann problems, and the I think the Kelvin-Helmholtz, no, not the Kelvin-Helmholtz, the Gaussians, the initial conditions, Gaussian initial conditions. And then we checked after fine-tuning on this problem, well, is it really the pre-training dataset that matters here? And is it really the quality and the diversity and the richness of features in the pre-training dataset? Because we said the data distributions we took out from the pre-training dataset for this less diversely trained model are the most rich ones in our opinion. And it seems like it is the case that this richness and diversity really matters. And when you compare it to just when you reduce to half of the quantity of the pre-training data set and then fine-tune, we are really able with our pre-training data sets so the model is really able to utilize the features from the pre-training data set. As you can see, with just half of the quantity, we can see that these smaller scale features in the pressure are resolved well. The vortices are resolved better in terms of when you look at the poorer pre-training data set. So it really comes down to quality in the pre-training data set. That's basically what we found. And it's not just this problem, you can also see it in the other problems. And it also boils down in the errors. So if you just look at these scaling plots here again, these two comparisons, it's really worth mentioning that, noting that pre-training dataset quality, and not just quantity, but quality matters. And that, I guess, this has been shown in many other works and with LLMs now as well, where maybe it's worth noting the Microsoft Phi model, which is much smaller, but the quality of the data is much higher. So we can really see this here for PDEs as well. So, okay, now we've seen visually, we've seen a fluid dynamics problem. Let's go to something different, the reaction diffusion type Alan-Kahn equation. So we have this kind of mixture of signs as initial condition, and then we fine tune on our trajectories, not many. Again, here we have the ground truth when we fine tune on one trajectory, 4, 32, and 128. And here it's worth mentioning, as I showed earlier, we have to exchange the embeddings. So the embeddings are trained from scratch because the variables are different to our pre-training task. And it's different physics. Makes sense, I guess. And as you can see, with one trajectory, even though you have a lot of artifacts going on because the embeddings are trained from scratch, you are able to resolve what's going on. So, and this also boils down in the errors, by the way, if you look at the scaling plots. So you really are able to, the model is really able to adapt to this new physics during fine-tuning. And you can really see that this reaction diffusion type of equation is learned very quickly. And yeah, we are, I guess, compared to the other models, kind of good. And you don't really need many samples to reach 1% of median relative L1 error, here, as you can see. So 32 samples, 32 trajectories is enough during fine-tuning to get 1% of error at the final time. So we always evaluated the test at the final time. So there's no mean over any trajectories. It's just the final time because it's the hardest task because of error accumulation. So and then you could say, okay, maybe the model is forgetting. Maybe the latent model during fine-tuning, because we fine-tune all parameters, is forgetting and it just learns the new physics. It's not that complicated. So maybe it's not the pre-training data that is going on here. So, and that's something that's not in the paper yet. You could answer the question, why do we even have to fine-tune all the parameters? Why not just freeze the latent model and then check, maybe the representations from the latent model from pre-training are enough to learn, the new physics are already in there, and check that. So we just train the embeddings and the recovery parameters and also the time embeddings because the time scales may be different, and compare that to what we've seen before. So this is what we've seen before when you fine-tune everything. And you compare that to the frozen latent model. And also there, you can see that, well, still you need a little bit more trajectories because again, the embeddings have to be trained from scratch. But with 32 trajectories, you get kind of visually at least the same results. And it seems to know, the latent model seems to have a gist of what's going on. So we kind of are able to really transfer from fluid dynamics to different physics, which is not clear a priori, in my opinion. And again, well, it makes sense in errors. Freezing the latent model is a bit worse because, well, you have less parameters to tune. Maybe to give an idea of how many parameters it is. So the model that we used here has 160 million parameters overall. And when we fine-tune all, well, it's 160 million parameters to fine-tune. And when we fine-tune just the embeddings, it's about 250,000 parameters, so a lot less. And then compared to FNO, well, we are still better when we just train the embeddings. So maybe, well, we could say this problem is potentially too easy. Let's go to something very different. And then we can have a look at the Poisson equation, which is, as I mentioned, time independent, and we have a time dependent model. In this case, we will incorporate time through the long time limit. So we will give a very long lead time during training. Just tell the model that through this kind of procedure that we are kind of working with a time independent problem now. So we kind of learn from the source term to the solution to the Poisson equation. So here again, ground truth, fine-tuning with one sample, 16 samples, 128 and 512. And here again, we fine-tuned all parameters. And as you can see, as you give more samples, the model has a gist of diffusion, which was not seen during pre-training. So this is different. There was no like diffusive diffusive action going on during the pre-training. So this is really different to what we've seen during pre-training. And as you can see with one sample, we kind of output the identity more or less, which makes sense if you look at the loss function, use the relative L1 loss. So it's good for the model if it outputs the identity in this kind of equation. But with more samples, it knows that it has to diffuse this this input, the source term, to get to the solution. And now you can ask the same thing. Can we utilize the pre-trained model as is? So we just freeze the latent parameters and just train the embeddings, because again, we have different variables here from pre-training. And also there, with some artifacts, of course, it's able to, or it already knows diffusion because we're not changing anything in the later model. And also here, Poseidon an error. That is still higher, but maybe the important thing here is that it's qualitatively, it knows what's going on. And then we can also look at maybe now we had different physics. What if we add physics to pre-training data? So we add a scalar tracer that we just let passively advect, that is just passively advected by the flow. And then we did the same, fine-tuned all parameters. Again, ground truth, one trajectory, 4, 32, and 128. As you can see, with more trajectories, it learns. Again, here we have to retrain the embeddings because there's one more variable going on. It learns that this tracer is passively advected by the flow, and the flow is also very well reconstructed. And then if you freeze the latent model, again here, it's new physics that it has never seen passive advection. It's also able to do that. So there potentially is something, the model has some sort of understanding of physics. Maybe that's a bit too much to say, but it seems like it knows what's going on. It can generalize to different types of physics, as we've seen. Again, here the errors are much lower than ethanol. And well, if you freeze the latent model, it makes sense because it doesn't have the high capacity, that the error is a bit higher than not freezing it. So to circle back to the initial question we asked, is it even possible to build what we would call a foundation model to learn solution operators to PDEs? And yeah, as I said, it's not trivial because you can't scrape the internet for data. We have to build it ourselves. So yeah, it's not very straightforward. But as we've seen, we just pre-trained on fluid dynamics, and the richness in the data seemed to be enough to be able to transfer to unseen physics. So I guess we can safely say with this kind of question, yes, and well, we can even generalize to something that was not seen. So yeah, I guess there's a lot more to explore and to test out. I mean, we had a lot of downstream tasks, but there's a lot more you could do. So that's why well, makes sense to open source everything. We have all the pre-trained models available. You can download them easily. We have all the data sets available. Open source, the code is completely open sourced and available. So if you're interested, please go forward, try it on your own data. It's very relatively easy in the code to plug your own data in and then use our scripts. Otherwise, if you don't want to do that, it's very easy to get the pre-trained model from the code. There's not much like you have to go to some website and download it and put it in something. You can just use, because we integrated everything in Hugging Face, you can just use basically 2 lines of code to get the pre-trained model and then start developing your things. Yes, and if you have any questions, if you want the links to the paper, to the model and the data sets, you can scan the QR code or go to the link where we will have all the other URLs going on. And if there are any questions, I'd be happy to take them now, and then we can maybe go over to the GitHub repository. And
thank you very much, Mike. This was again very comprehensive. Again, thank you. All right.
I
Yeah, there
guess.
is.
So as the question is, you mentioned you use the whole trajectory for training if you have input to the model at some timestamp tn minus 1, and does it make sense to predict output tn based on t0 only? Do you always include time steps where input was provided? So we always include just one time. So the input is just one time step, as is with a conventional solver. And then you give a lead time, and then you should get the solution at this lead time. So there's no like time aggregation or something going on, which if you look at it from a practical perspective, doesn't make sense, because normally if you want to use this model, you will start with your initial condition as with your standard solver. Your numerical solver also starts just with the initial condition and then goes forward. And during training, well, we use all kinds of combinations of the trajectory. I mean, yeah, so the idea was to get something that mimics the classical solver and not utilizes a sequence of snapshots, because yeah, in a practical sense, if you want to deploy this model, you don't want to go forward, deploy your classical solver for 20 time steps, then aggregate these time steps, and then start your simulation using your model, and then you can just directly use your classical solver.
Thank you. So yeah, there's a question in the room, the physical room here, and then we'll get back to the online.
Yeah.
Hi, Max. I think this is a very good piece of work related to foundation model. And my question is about the operator learning. So we know that the operator learning algorithm is trying to learn mappings between infinite dimensional function spaces, which are continuous objects, right? But in reality, we can only have access to the discrete representations in digital computers. So how can you make sure that your results are not sensitive to your specific discrete samplings? In other words, I know the work from the work Reno, right? From representation equivalent neural operators from your advisors. Then is your scalable operator transformer Reno?
We are able to be invariant to the resolution. So we train on a computational grid that is the same overall data, but during testing you're able to be you're invariant to resolution. Yes, so it's a win. I would say so.
Yes, yeah, I saw that in your paper the test resolutions are always coarser than your fine-tuning resolution, right? So what about the performance of super resolution?
We didn't test that yet.
Oh,
we
okay.
I would have to try that. It's we had a lot of data sets, and you have to handle all of that, and some things just get lost, I guess.
Thanks. Thank you.
Next thing.
I had another question as well.
Yeah,
so while training, you pass in like multiple lead times, right? Because of the all-to-all training strategy. So at inference, how do you decide at what DT you want to like do the rollout?
Sorry, I didn't.
So
I gotta speak slowly.
at inference time, how do you decide what time step do you want to choose when you do the rollout?
Yes, so this is, I guess, something for future work a little bit. This was kind of empirical in this work. We just tested, and we've seen that for some problems, for example, for the wave equation, it makes sense to just do a single step rollout to the final lead time. For the fluid dynamics problems, it was better to do an autoregressive rollout with the smallest step size during training that was seen during training. But in general, you have a continuous mapping in time, so you can do anything. But it's a bit up to future work how you want to really do this or implement this in a solver that you would deploy in the end, because it depends on the data set. Oh, that's what we found. Very much. And well, if you've seen that the dynamics changes a lot, you can do bigger steps, and with the as seen in the wave equation, for example, if you look at this plot here, for example, the input and the output are very much different, then it was better for the model to just do a single step prediction instead of an autoregressive forward.
Interesting. So I know you did mention that there's like no CFL condition essentially that comes in because it's not technically not a numerical solver anymore, but implicitly, do you still think that there's like beyond like the DT that we can, you said that the rollout is for the, at least the Navier-Stokes problems are with the DT used for generating the training samples, right? Like,
Yeah, so
is
we
it
have,
possible? Yeah, is it possible to just use larger DTs and are the solutions still stable?
you can use other DTs as in the training. I mean, I guess not smaller than the one you've seen. I guess I didn't test it yet because well, we didn't have the data yet to test it. But bigger DTs are always possible, but because you're during training, you do all kinds of possible lead times, from the smallest to the biggest. So the model kind of knows what's going on in the end, in terms of the lead time.
Yeah, thank you.
Right. So do you want to address the two questions online?
Any thoughts on generalizing this approach to SDs? Well, we didn't think about it yet, but it's definitely something to do in the future, I guess. I have no clue how at the moment, but I mean, there are many smart people out there, so you can try. What is the resolution of the images that you used? It's
Max, on that first question, right? Could you just imagine, sort of the obvious way in which you extend standard neural networks to Bayesian neural networks, right? Where in addition to the mean that you're predicting here, right, at any point, right, you also predict the variance, right? That could be sort of an easy way to extend this to SDEs.
Definitely, yeah. I mean, it's probably easy to try out, so it would be worth trying out. Maybe we can do that. But yeah, it's in the end, it's a neural network. So all of these classical approaches that we've seen in the literature should maybe work there as well.
Yeah, we could give it a run for a couple of days in the hackathon, maybe, depending on our goals.
We need the data. We need the data.
Yes.
That's the key, and data is always the key.
Toy problems we can generate. I don't think it's a big issue. Okay, can you take the next question online?
Yes. So the resolution of the function discretizations we used was 128 by 128 on all the problems. So we didn't go bigger because, well, and we also did just 2D problems because, yeah, it just blows up computationally as you go much bigger. But the compressible data was generated at high resolutions. One could potentially also train it with higher resolution. And one thing to note that with the twin transformer we used here, we can also fine tune with higher resolution. Turbulent flows with this technique. I'm not sure what you mean with solving turbulent flows. I mean,
he means chaotic, more chaotic 3D, those types of problems.
I think so, yeah. I mean, this is just a feeling, but we've already seen quite turbulent flows. Maybe if I go back to the data. Here in the top left. This is already quite turbulent, I would say. In 3D, yeah, it just gets more complicated. But that's also something for the future, I guess. And yes.
Yeah, there are people who do turbulent channel flows and a few other flows with these types of methods, not foundation models, but these operator learning methods. So yeah, I don't see fundamentally any challenges, but yeah, practically there may be a few.
Yeah,
right.
practically you'll always have some sort of diffusion going on. So
Yeah.
it might be
All right.
complicated. Then you need a higher resolution, and then the classical problems come in.
Correct. And the next question is, can you explain why you use the L1 rather than the L2 loss?
So I think the main motivation was to resolve discontinuities better. I mean, we have a lot of shocks in the data, small scale vortices, stuff like that, and also BL1 loss is a bit well, not so nice to use, so it's a bit harder to get a lower error there. Yeah, that was, I think, the main idea. But we could also test it on the L2, but I think it will hold up quite well.
Great. All right. So yeah, thank you again for this very comprehensive outline of your paper. So yeah, we'll be back at 2 p.m. Online with the next tutorial being on data tokenization and some practical issues. But Max, thank you very much again. I'll see you next week.
So we're not going about on the GitHub.
You can walk through it. I thought that was your last slide, but yeah, if you want, you can just give a high-level overview of the
It
code
depends.
walk through GitHub. Yeah, please go ahead. Yeah.
Okay. So yeah, as I said, we have everything open source. So if you go to our GitHub, you can install the pack. If you clone the repository, you can install everything very easily. And then we have a training script, we have a trainer. So when you have your own data set, you can go in and put this under problems, Scott/problems. Put your data set there and then implement the dataset class. It's very well documented, I would say. There's a question, just open an issue, and derive from one of these two base datasets, either base dataset or base time dataset, depending on whether if you have time independent or a time dependent problem, and inherit your class. It's very easy, probably, and then you can just use our scripts to fine tune the model. And as I said, if
Max, can you increase the
it's you
the
can see
font
it.
size? And maybe a couple more, maybe one more. Yeah.
So didn't do it here. So you just install it easily and then plug in your own data set, which should be quite straightforward. Write your own configuration file for fine-tuning, and then go forward and use our training script to fine-tune the model, which will automatically download pre-trained models if you specify it. Yes, and as I said, we also have a trainer, so you can also do inference with that trainer, and a script if you want to. And yeah, every model is available on the Hugging Face hub, so you can go there and have a look at the model cards. Yeah, well, I guess the paper is more straightforward. And also our data sets are available here. So if you're interested, you can use them very easily. Just go there. You can use the Hugging Face hub command line interface to pull the data sets. And since it's not a language data set, we had to do a workaround, split the data, and then you have to assemble it on your machine. But once you have the data, you can also train your own models with that. And I guess, yes, it's many data sets and yeah, a lot to play with, I would say. Yes, and apart from that, I guess we can have a look next week in more detail. And yeah, always if there are questions popping up, just open an issue and we will hope to get back to it. Yes, with that, I hope there are no questions anymore and we can conclude the session.
Yeah, great. Thanks, Max. This is great. And yeah, I think there's a lot of exciting avenues to pursue in the hackathon here. So excited about that over the next couple weeks. All right. So thanks, everyone. And then in the afternoon session, we'll continue and we'll have a very detailed code walkthrough on data and tokenization. So see you at 2 p.m.